This hour will introduce another topic in network layer called control plane. We have already talked about there are two different planes of network layer, which is control plane and data plane. And data plane is used to forward packet when packets arrive at the router, and router have to decide which port it need to forward it to. And the control plane is to manage the routers and run routing algorithms so that the routers and its neighboring router can work together to determine what is the best path to route different packets. Okay. So the goal of control plane is to understand the principle behind network control plane, and then we will introduce two different traditional routing algorithms, and we will talk about how routers are managed and set up. Okay, and we will talk about some network management protocol, which is ICMP, and the configuration. But we will not. But since I think students should focus more on data plane, because when we route packet, okay, in a subnet, so we have a lot of different mechanisms and different tools to help us to configure the subnet, and that is what we can do in our home network, in our ADSL cable modem, and in campus subnet. But for students, I think to manage routers and a router or many routers, this job belongs to the network administrator, which is the employee administrator and computer center in campus. It is a little bit difficult for students to play with these routers to do such kind of configuration, and it is not that easy for students to learn how actually a router works. So we would simply just introduce some simple concept of control plane. We will not tell you what exactly the protocol they use, what is the format is. We will not do so, because students or what we say MS students, they may not be able to play with real world routers. Okay, so at the right hand side, of course there are some protocols, routing protocols, OSPF, BGP. We will introduce a concept, but we will not go into the details about what is the format, how do they exchange messages. We will not do those details. Okay, but IP protocol, UDP, TCP, or HTTP, that is what we are familiar with. We should be familiar with. So we introduced how they work. But OSPF, BGP, those protocols, we simply just introduce the concept. Okay. So the first topic is routing protocols. We will introduce two protocols: link state and distance vector. Okay, so here is the routing protocol. The goal of routing protocol is to determine a good path, okay, or say it's routes from the sending host to the receiving host through the network routers. But as we mentioned before, in the subnet, we when we send packets out from the sending host, usually in the subnet, okay, all the network interfaces in the subnet can receive the packet, okay, but the edge router has to determine how to relay, how to forward, how to route this packet to the entire internet, hop by hop, and to the destination subnet. Okay, the edge router will receive the packet and forward the packet to its destination to its subnet, and all the subnet, all the hosts in the subnet can get the packet, okay, by using broadcast. So usually when we talk about good path, we talk about how a packet is routed from the sending subnet, the router of the sending host to the destination host. Okay. So the path is a sequence of router packet traverse from given initial source host, and of course to its corresponding edge router, and to the entire internet, and to the corresponding edge router of the destination host, and then to the final destination host. Okay, it is a path, and we have several different metrics to determine what is good. Okay, and as you can see that to determine a good path, okay, for example, cost. Okay, if it takes, for example, 1 cent to send the packet from one router to the other router, okay, maybe in another path it costs that or more. Okay, so to find a good path, that means we have to find the minimum cost of a path. Okay, sometimes the good is defined by fastest. Okay, for example, one path is more congested and the other is not, so we will take the path or take the route which is less congested. Okay, so your packet will be delivered to the destination more quickly. Or it can be defined by hops. For example, it takes 15 hops from your source to your destination, but the other route only need, for example, 10 hops. So maybe we consider that 10 hops is more efficient, or we say least cost. Okay, so it's really depend on how you define good. So we have several different metrics, and but usually in current internet, we usually use number of hops to determine the cost and to determine what is a good path. Okay. So here, since the network is very complex, so usually when we talk about how to determine the path, we use a more systematic, more mathematic way to describe this question. Okay, we use a graph to describe a network. Okay, so at the left-hand side, you can see that here we have a graph, capital G. Okay, it contains two sets. Okay, two sets. The first set is big capital N. Capital N means how many different nodes, how many different routers in this graph. Okay, so we can see that N is a set. Okay, it includes I think 6 different routers, U, V, W, X, Y, Z. Okay, you have to define how many nodes, how many routers in your graph. And next part is E, capital E, which means age. That means how many different links you have in this graph. Okay, I think in this example, I think it has 9 different ages, 9 different links. So you have to specify the node of this age. For example, UV means we have an age between node U and node V, and so on and so forth. Okay, so if there's no age between 2 nodes, you don't have to write it down. Okay, you simply just write how many different links, how many different ages in your graph. Okay, so that is the definition of your graph. Sometimes we use another word, topology. Okay, topology specify the node and the age and their connection. Okay, we use the word topology. Okay, right here we have another definition as cost. Okay, no matter what cost you're referring to, For example, you can use hops. You can use the number, the amount of money you spend when you transfer a packet from on this link. For example, you can define the cost as the level of traffic congestion level of the traffic. It really doesn't matter. In mathematic representation, we simply just use a number on the edge to specify the cost of this edge. Okay, so we have the question right here is, how do we define how do we find a good path from U to Z? Okay, U is the sending host, sending router. Z is the receiving router. Okay, how do you define? How do you find a path? Okay, with minimal cost. Okay, so CWZ means that is 5. That means the cost between W and Z is 5. And if there is a CUZ, take a look at this figure. CUZ, there has no such links, so the cost of CUZ is infinite. Okay, so that is. So that is the mathematical definition of a graph and its age, its nodes, and its cost. Okay, so before we introduce these two different routing algorithms, you have to think about two different things. One is the information. Okay, it's right here and here. Okay, global means, does your algorithm need global view of your topology? So that means all routers have complete topology and link cost information. For example, in this graph, all these 6 routers, they all know this topology, and they all know nodes information, age information, and the cost information in this graph. So that means we have global view. So you can think that you, as an oracle, you have the complete view. So you can design an algorithm to find the minimum cost path from U to Z. Okay, that is global view. But you have to think about one thing, that it is not easy for all the routers in the graph to share all the information, because in this graph we have only 6 routers and 9 paths, right? So it is relatively easier to share all this information because the information is limited. But in a very, very big network of routers, maybe you have thousands of thousands of router, and even 10,000 of links. So it is not that easy for all those routers to share information of this graph, because you have to exchange a lot of information to make sure everyone knows the information of this graph, this topology, and these costs. Okay, it is not easy. So on the other side, we call it decentralized. That means we have a decentralized algorithm on those routers. They have to iteratively compute the best path from U to Z. So only neighbors exchange information between neighbors. They don't have to share the information across the entire networks. So it is much more easier for lots of routers to compute a good path by using such kind of a decentralized way. Okay, but if you have a very small network and all the networks, the number of routers is manageable, you can use a global approach to compute a good path. But you have a very, very large decentralized routers, and they are not under your control. It would be better to use decentralized algorithm. Okay, so that is the difference. And later we will introduce link state and distance vector, and one is global. One needs global view, and the other distance vector only need decentralized view, decentralized information. Okay, so that is the first part. And the second part is how fast do routers change. Okay, the static means routers, those routes. Okay, you can see that this graph, and including the nodes, the number of nodes, the links, and their cost. If it changes a lot, okay, if it changes a lot, we have to compute a new good path more oftenly, right? But if this topology is very stable, that means once we compute the path, the good path from U to Z, it usually, okay, often it does not changes, right? So it depends on how fast your routers, your route, your link, your cost changes over time. So we call it static. That means routes changes slowly. We call it dynamic, means the router changes more quickly. So it takes time. So it depends on your topology and your network situation. For example, in our campus, maybe we have only limited routers, and those links does not change quite often. So for those routers, we can compute the routes, okay, and it will not change too often, okay. But for example, in the internet, some routers might go offline, or power shortage, or some outage, or some situation might happen. So routers may change its route quickly. So I have to run the algorithm more oftenly. Okay. So the first part is the first routing algorithm called link state. Okay, right here. Link state is designed by a computer science professor. I think it is a professor called Dijkstra. Okay, Dijkstra. So Dijkstra designs this link state routing algorithm. So it is a centralized routing algorithm. So that means the topology, the link cost, the node information, the edge information are known to all nodes. Okay, those information will be broadcasted by link state broadcast among all those nodes. So of the node who runs the link state routing algorithm have to share its information to all nodes. Okay, so all nodes have the same information. Okay, so after they get all those information, they have to compute least cost path from one node, okay, to the other node. But right here it says to all other nodes. That means when you run this algorithm, link state, Dijkstra's link state routing algorithm, okay, and take this example. If you want to compute the path from U to Z, okay, but after you finish computing, this routing algorithm, you will get the path, the good path from U to V, U to X, U to W, U to Y at the same time. So right here it says it can compute the least cost path from one node source to all the other nodes. Okay, if you run Dijkstra's link state routing algorithm. This routing algorithm also has another name called shortest path algorithm. So shortest path algorithm, okay, that is the algorithm invented by Dijkstra, and Dijkstra use it. We use it to run link state routing algorithm. Okay, so after you get all the shortest path from a source to all the other destination, you can write down your forwarding table. Okay, so before we explain how this algorithm works, we have to go back to chapter 4 because we have 3 additional pages. Okay, so that is how a forwarding table looks like. Okay, left hand side is a destination address range, right hand side is the link interface. So that means if a router get a packet, and it will check its destination IP addresses and see if it falls into the range of, take this example, 200.23.16.0 and 200.23.23.255. If the destination falls into this range, and that means this packet should be forwarded to link interface number 0, and so on, so forth. Okay, but if your destination address does not fall into any first 3 destination address ranges, then we have another rule called otherwise, or we call it default route. That means your packet should go to should be forwarded to link phase number 3. So that's very simple. You simply just take a look at the destination IP address and check it against with the forwarding table. See to check see if it falls into certain ranges. Okay, and you should forward this packet to the corresponding link interface in the forwarding table. Okay, here I draw a figure right here. That means usually when you in your home network, okay, you have your LAN, right? For example, you use a NAT server, so you have a private IP address like 192.168/24. Okay, you have a private VAN. Okay, and you're adding a modem, and there should be a router right there because your LAN, your boundary should be a router. But it is a very simple topology, right? So basically, as this is a modem, and its router should have only 2 interfaces. One is to the LAN, the other is to the internet, which is attached to the it is a modem. So your forwarding table will be very, very simple, such as if the packet destination is 192.168/24, and it should goes to interface number 0, and otherwise it should go to the internet, which is interface number 1. So basically, in your home network, your indeed it is a router, but I think it is a very, very simplified router. It has only 2 routing rules in this forwarding table. Okay, either forward a packet to your subnet or forward your packet to the internet. Usually we don't actually run routing protocol on your home router because it is very simple. So you have only you can only set up 2 forwarding 2 entries in the forwarding table. It is good enough to do routing. You don't really have to run routing protocols because routing protocol is very complex. But write such kind of 2 very simple rules is much easier. Okay. The other problem is about what if you have a destination address that falls into that matches 2 rules. Okay, take this one as example. The red one, example number 1. Okay, you take a look at the red part. Okay, it starts with 0110, right? 0110. Actually, it matches this one, and it matches this one too. But it's very simple. You simply just forward this packet to the longest prefix rule, which is number. Oh, sorry, that is 011. That should goes to link phase number 0, and these 2, okay, will match the second and third rules. Okay, but you simply choose link phase number 1 because it has a longer prefix matching. Okay, this is quite simple. Okay, that is just some explanation. Okay, let's go back to here. Okay, we will introduce some concept, and we simply just jump into this example. Okay, it is a little bit complex, so I will draw it again. Okay, so let's take a look at this graph. Okay, we have nodes, right? U, V, W, X, Y, Z, and we have some links between them. Okay, now we have a question is that how do we find a shortest path, which means a path that has minimal costs, summation of the cost, okay, from U to Z. Okay, we have 6 different nodes in this graph. Okay, so remember one thing, we will have 6 steps. Okay, 6 steps. So we mark it as 0, 1, 2, 3, 4, 5. We have 6 steps to deal with how to find the shortest path between U and Z. Okay, so here we have a notation which is capital N prime. N prime means how many different nodes has been processed, has been calculated by using Dijkstra's shortest path algorithm. Okay, so as you can see that each step we will include one node. So at the very first beginning, we have node U in N prime. Okay, at step number 0. Okay, that is the okay. So after you include one new node in N prime, then you simply just draw a line, something like that. That is step number 0. That means I already include a new node U in N prime. Okay, so take a look at this line. If it touches the edges in this graph, then you can simply just draw that some marks on the graph. Okay, that means okay. Let's take a look at this very first node, which is V. Okay, and the 7U means, can you go to node V across this boundary? Okay, the answer is yes. And how did you across this boundary to reach V? That means you take 7 costs and through U, and then you can cross the boundary, the orange boundary, to U. To V. To V. Okay, so 7U means I can cross this boundary through U, and the cost is 7, and I can reach V. Okay, so next, this one, that means W. Okay, could you cross this boundary to W? The answer is yes, right? The answer is yes, because you can cross this boundary through this link. Okay, so you write down 3U, right? You can reach W through U, and the cost is 3. And next one should be this one, right? 5U, because the link between U and X is U. It's 5. But you cannot reach Y and Z through this orange boundary, right? So you simply just write down infinity right here. So that is your step number 0. Okay, number 0. So next step, okay, is that you simply select the smallest value right here. 3 is the smallest one, right? So draw this one. Okay, and that is W, right? So you put W in your n prime at step number 1. Right, step number 1. Because it's the smallest one. Okay? And again, now n prime has U and W, right? So you have to draw a new boundary such as this one. So that is boundary step number 1. Okay? And again, there are several different lengths that can across this boundary, right? So again, right here, think about one thing. It is possible to reach V through this boundary. The answer is yes. You have two different lines. One is right here, the other is right here, right? That's right here. So think about one thing. When you include W within this red line, okay, it is possible to find a new path that goes through W, and it has smaller cost. The answer is yes, because to reach V, okay, original, you have to go through U, and the cost is 7. But currently, you can go through W to reach V, and the total cost is 3 plus 3. That is is smaller than 7. So simply write down, yes, I can go to V through W, and the total cost is 6. And again, to X is right here. What if I go to X through W, and then you can see that the total number is 7 if I go to X through W. But 7 is larger, so we don't have to update it. Okay? And again, can we reach Y through W? The answer is yes, because we have a edge that across this red boundary, right? The answer is 8, right? So 8 and 3, the number is 11, and go through Y. And through this red boundary, we still cannot reach Z, so that is like this. Okay, so that is. So next part, again, we select the smallest part, which is X. Okay, so we add this X to here. So next time, so right now you draw a boundary like this, right? So now we have include X right here, so X can reach this one, that is. Okay, so let's take a look at V. Can we reach V through this boundary? Yes, it's right here, but it is not through X. So include one more X. It does not help, so we simply just write 6NW. Okay, and how about Y? Okay, right here, we can reach Y through X. But currently X, the smallest, the X is 5, right? From U to X, this is 5. So 5 plus 7, that is 12. So to Y, if we pass through X, the total cost is 12. But actually, Y can be reached by W and using only 11 costs. Okay, so we don't have to update it. Okay, because at X does not help. Okay, and last part is, can we reach Z through X? The answer is yes. So that would be 5 plus 9. That is 14. And again, we select the smallest one, and then let's stop V. So we add V right here, and we can draw a new line right here. So we include new V, right? So currently we have this line, this line, this line, this line. But as you know, V only can reach Y through this blue boundary, right? So let's take a look at if V helps. So let's take a look. To reach V, okay, to reach V, it takes 6 cost. And to reach Y through V, the answer is 6 plus 4, so that is 10. Okay, that is less than 11W. So that means because I include V, so I can reach Y through V, and the cost is 10, which is less than the previous condition. The previous one is go to Y through W, and it takes 11 cost. Okay, and again, because V is right here, is not connected to Z, so it does not help. So the answer is right here. So again, we select the smallest one, and that is Y. So we include Y here. So next part is right here. Again, we include new Y. Can I go through this green boundary through Y to Z? Yes, we can. And the amount of cost is 2. So Y is, let's take a look right here. The Y is 10, right? It takes 10 cost to Y, and we add 2 right here. That means you can go through Y to Z with 2 additional costs. And then that's all. So you can use this algorithm to find out what is the shortest path from the U to all the other. Actually, the original purpose is to calculate the shortest path from U to Z. But when you do so, when you do the stack trust routing algorithm, actually you can compute all the shortest paths starting from U. Okay, I think you have to take some time to run this algorithm by yourself. And here we have another example right here. So if you need to, you can do it by yourself to check if your table looks like exactly the same as the example in the textbook. Make sure you know what is the actual step of Dijkstra's routing algorithm. Okay, so again, let's take a look at these two notation, dV and PV. dV means what is the distance, current distance. Okay, so that is 7, 6, and 6. Okay, PV is what is the previous node you go through. So that is right here. So let's go back to the first page. First one is CXY. That means the cost between X and Y. D means the current estimate of the cost path from source to destination V. P means the predecessor node along path from source to V. And prime means the set. Okay, and it should include all the node. Okay, step by step. And at the end of the step, all the nodes should be included in prime. So in this algorithm, we iteratively execute the computation. Okay, so if you have k nodes and you have to run k iterations, so you know less cost path to k different destinations. Okay, so try to run this algorithm, okay, by yourself. Okay, so we have some discussions right here. So the algorithm complexity is that if we have n nodes, Okay, so we have n iteration as we explained before. So we have n iterations, but for each iterations we have to do comparison, right? Take a look at this table. Okay, in step number 0, we have to compute 5 different values. In step number 1, okay, because we have exclude one node, which is W, so we have only need to do 4 comparisons, and 3 and 2 and 1. Okay, so if you have n right here, you have n nodes in total, you have to do n times n plus 1 divided by 2. You have to do that amount of comparison. So the big O is n squared. That is a big O n squared complexity. Okay, because the most significant part is n squared. Okay, so we say it is n squared complexity. Okay, of course there are some more efficient implementation, but we don't discuss it right here. The other thing is about how many different messages should be broadcasted to the entire graph. As we mentioned before, because it is we say it is a global routing algorithm, so all of the nodes should have all of the information about cost, ages, nodes. So at least each router must broadcast its link state information to all the other n routers. Okay, so the overall message complexity is n squared as well, because the first router has to send n messages to all the other routers. The second router has to send a messages. The third, still the same. The last router, the nth router, still has to send n message to all the other routers. So the overall message complexity is big O n squared. Each router need to send n messages to. Okay, so that is the discussion. And here we have a very interesting problem of Dijkstra's algorithm that try to understand that. Okay. Okay. We have 4 routers right here: A, B, C, and D. And B, C, D. Okay. They all send their packet to router A. Okay. Take a look at it. This figure T0. That means at time 0, at the first beginning of time 0. Okay. B, C, D, they would like to route 1 unit of packet to A. C would like to route amount of packet, which is epsilon E. Epsilon means a small amount. Okay. D also need to route forward 1 unit of packet to A. So that is 1 epsilon and 1 unit. Okay, and epsilon is less than 1. Okay, far smaller than 1. Okay, so so at the first beginning, because there has no traffic on this network, so B decide to send its 1 unit of packet to A in this direction. Okay, at the first beginning of T0, because there has no traffic, so D randomly select a path, for example right here, to A. And for C, and again at the first beginning of T0, time stop 0, because there has no traffic, so C can randomly decide to send a packet to the right hand side or to the left hand side. This is okay, and it decide to send it to the right hand side to B, and B will forward it to A. Okay, so at the end of slot 0, okay, we have 1 plus epsilon and epsilon on this link. You have to notice that in this specific graph, the link are bidirectional. You can see that we have the link is bidirectional, so the cost is bidirectional. So I should say that the link is bidirectional, but when we calculate the cost on this link is unidirectional. Okay, so in this direction, the cost is 1 plus 0, because currently the traffic from B to A is 1 plus epsilon, but the traffic from A to B, this direction, it is still 0. Okay, so the traffic, the amount of traffic right here is unidirectional. Okay, so the next time T1, if we calculate our routing algorithm by using the congestion level, and it is defined by how many traffic on this link. Okay, if the definition is the cost on the unidirectional link is defined as the amount of traffic on this link. Okay, and at T1, again, when new packet arrives at these 3 routers, and they are still 1 unit epsilon and 1 unit, but they have to do calculation to determine what is the good path from B, C, D to A at the first beginning of time slot number 1. So they take a look at the result of slot number 0, which is the red numbers which I wrote on the link. Okay, let's take a look at B. B, okay, at the first beginning of T1, it takes a look at T0. It says, okay, the link between A and B, the link between B to A is 1 plus epsilon. But if I take another B take another route from B to C, that is 0, right? From C to D, the cost is 0, and from D to A, the cost is 1. So at the first beginning of T1, B believes it would be better to send the 1 unit traffic to C, D, A, which is much better than B send it to A directly, because the cost is less, right? Because the cost is less, that is 1. If B directly send the 1 unit of blue traffic from B to A, the cost is 1 plus epsilon. So B will send this amount of traffic to C, and C will help B to forward to D and to A. Okay, and again, for C, at the first beginning of T1, it look at T0, and it will say, okay, I have epsilon traffic to send, but it seems like C send the blue traffic to D and to A, which is shorter, or we say has less cost. So C will send the epsilon to here, and again D will send its blue traffic to here. So at the end of T1, all the traffic from B, C, D will send to the left-hand side and to A. Okay, so next time at T2, when BCD has a new traffic, the red traffic comes in, BCD will believe, okay, maybe they have to send all those traffic to the right-hand side, forward it to B, and B to A, because at the end of T1, all the traffic goes to the left-hand side. So it causes a problem that if your link cost depends on traffic volume, sometimes it changes because of you have a epsilon in your network. This epsilon, well, changes the total cost, right? So sometimes you think traffic should go to the left-hand side, and sometimes you think the traffic should go to the right-hand side. That is because when every time, at every beginning of the time slot, you have to take a look at the previous time slot, the result of the previous slot, and all the traffic will go to the empty links. But when everyone thinks so everyone send their traffic volume to the empty links, and again, at next time slot, the traffic volume condition changes, and so on and so forth, so on and so forth. So it's not a good idea to do so. But Dijkstra might have such kind of problem. Okay, we stop right here. It is the Dijkstra. We'll talk about another algorithm next hour.